What if I told you that when you're driving your car and you come up to a red light, if you drive fast enough, that light will appear green? It's actually possible to do. Now, that does not make it legal, and you would have a very hard time traveling fast enough to make it do this. But it is possible based off something called the Doppler effect. And Sheldon Cooper explains this in The Big Bang Theory accurately, as he says it's the apparent change in the frequency of a wave caused by the relative motion between the source of a wave and the observer. Let's explain what that means. We're going to use light first. And so this is a person's eye, and you're able to detect the wavelength of light to determine color. The longer wavelengths of visible light are red, in between is kind of more green, and then short ones would be blue. So let's say this wave comes along and our eye interprets the wavelength of that to be red. So this right here is going to show what you see. Now, before we had this formula of V is equal to lambda times frequency. Now, the velocity of the wave, the speed of light is 3.0 times 10 to the 8 meters per second. So that's staying the same for any light wave. But if we have a longer wavelength, we have a decreased frequency. So that's what we're seeing this red light as. I'll go back. It's a long wavelength and a low frequency. So you can kind of see how often those peaks are kind of hitting that eye there, like now, kind of like that. So that's what it's going to interpret as red, that frequency and that wavelength. Now, if we went to a shorter wave like this, see this green one is a lot closer together. I'll kind of play that again. It's got a smaller wavelength, so when it's hitting the eye, the peaks are hitting the eye a lot more frequently. So again, the velocity is staying the same, the wavelength is decreased, and so the frequency has increased. And our eye interprets that to look like green, like we can see here. So the way that we can kind of change this is if we take a red wave, so a piece of red light, and we shoot that at the eye, but we're going to increase its frequency by moving the eye towards the light. So look at this, the eye is moving. You can see how now those peaks are hitting the eye a lot more frequently. I'll show it again. They're interacting with those peaks of the wave a lot more frequently than they were if you were standing still. So we've increased the frequency, and our eye is then going to interpret that as green. Now, you have to move very fast to do this, but that's what the Doppler shift is, a change in apparent frequency of a wave due to motion of the observer or the source. It says relative motion between the observer and the source. So if the person was standing in the same spot and the light source, whatever was shining that light, was moving as well, that would have the same effect. They just have to be moving relative to each other. I think it's easier to show the animation here with the person moving. And this works for sound as well, which is what we're going to look at most. So let's see, this person is sitting here, and this is some compressions and rarefactions of sound in the air. And we can see the frequency that is hitting the ear, like how often those lines are hitting the ear. And maybe that sounds like 444 hertz, which would sound kind of like this. And that's what the person would be hearing. But now we're going to move the person towards the wave, and we're going to see that those bars are going to hit that eardrum more frequently, and it's going to sound like a higher frequency. So let's just play that. He's moving towards it. Those bars are hitting his ear a lot faster, and maybe he's going to interpret this to be a frequency of 650 hertz if he was going quite fast, which would sound like this. So it's an apparent change in frequency based off motion, relative motion, between the source of the wave and the observer. And this is the formula that describes it. So this frequency over here is the frequency that we're going to hear. So I'm going to put here. All right, that's what the observer is going to think the frequency is. This is the frequency of the source. I'll just put it in here, source. All right, so that's what's coming out of, say, the speaker. Now what's in the middle here is a ratio between how fast the observer, that's what this O is, and the source are moving relative to the speed of sound, which is these two velocities right here. So the speed of sound. Now I have left two parts out here, and it's that on top it's V plus or minus the velocity of the observer, and on the bottom V plus or minus the velocity of the source. This is one of our most complicated formulas, so I'm going to kind of just try and simplify this a little bit. We have what we hear is equal to the source of the wave, and then there's this ratio in between. So let's just think that if there was no motion, all right, so if this was just the velocity of sound over the velocity of sound and the observer isn't moving and the source isn't, it's plus or minus 0, this whole ratio is going to work out to be just 1 because it's velocity over velocity. And normally the speed of sound is around 343. So you can imagine 343 divided by 343 gives you 1. 1 times the frequency of the source is going to be the same number for the frequency the observer hears. So that's if there's going to be no relative motion. Whatever the source is, that's the same as what you hear because this ratio is equal to 1. Now, when we would hear this frequency as a higher frequency than the source would be when this ratio is greater than 1. So how would that happen? Well, these numbers we don't change. The velocity of sound is going to stay the same, around 343. And then we have plus or minus. That's where the plus or minus choice comes in, because it's not actually always plus or always minus. You have to choose what it's going to be. So that makes this one a little bit hard. And we're adding or subtracting the velocity of the observer or the velocity of the source. Now, usually it's just going to be one thing that's moving. So let's create an example here where we have a speaker over here, and it's going to be emitting some sound, and we have a person maybe running towards that sound. In this case, the source of the wave, the speaker, is staying in the same spot. So I could get rid of this right here and say, okay, well, if I'm doing this calculation, let's say that the speaker is making a noise of 400 hertz. What's the person going to hear this at? Well, how we're going to work this out is these numbers, V and V, are going to be the same, 343 meters per second. And then the decision comes whether we should add or subtract the velocity of the observer. So first you have to think, is this person going to hear it higher or lower than 400 hertz? Well, kind of in those diagrams as we saw, if we're running towards the wave, the frequency that it hits the eardrum is going to increase. So we're expecting that we're going to hear this higher than 400. So that means that this whole ratio needs to become greater than 1 so that the frequency we hear is bigger than the frequency of the source. So then should we add or subtract the number on the top? Let's say they're running at really fast, 10 meters per second, right? So should we add 10 on the top or subtract 10 on the top? Well, I'm just gonna write over here, we have 343, 10 over 343. How I make this number greater than 1 is I have to add 10 to make the top number bigger. If I subtracted that 10, the top number would be lower and our ratio would be less than 1. So we need to know we're going to have to add 10 in that case. I know that takes a lot of thinking, but start with, is this going to be a higher or lower frequency? And would adding or subtracting make that number greater than 1 or less than 1? Let's switch it now to the person is running away from the speaker. All right, so they are going in this direction at 10 meters per second. Again, really quick. Well, if they're running away, we need to know that then the sound is going to be hitting their ear at a lower frequency because they're getting further and further away. It's not hitting their eardrum as fast. So that's going to mean that this frequency is going to be less than this frequency. How does that happen? If this ratio or that box is less than 1, okay? So the speed, again, is going to be the same, 343 over 343. And we said the source is not moving, so plus or minus 0 wouldn't matter there. We're just at 343. So how do I make this number less than 1? We know they're going at 10 meters per second. Do I add or subtract 10 on the top? I have to subtract. That's going to make this 333 divided by 343. That number is less than 1, and it's going to reduce the sound that we hear compared to the frequency that is produced. So that's how we're going to use this formula. First, consider which is moving. So what is moving? Either the source or the observer, and the one that's not, you can just put in 0, which is, I think, a nice way to clean this up a bit before you start. Second, what you should consider is the frequency going to go up or down? So it's frequency going to increase or decrease, right? Once we've determined that, we can look at if to make this increase or decrease, what does this ratio have to be? Does it have to be greater than 1 or does it have to be less than 1? So I think that's our third step, determine if it's going to be less than 1 or greater than 1. And our last step then is should we plus or minus to make that happen? And it's kind of nice that you can always check. If you got the sign wrong and say the person's running towards the speaker and you got it so they're gonna be hearing it at a lower frequency, well, that's not what I determined in the second step. So I know I have to go back and flip that. To look at the other scenario where the source is moving, we're gonna do an example here and actually calculate what we're gonna hear it at. So it says an ambulance is sounding its siren at 550 hertz and the ambulance goes towards a stationary observer at 15 meters per second. What does the observer hear the sound at? Speed of sound is 343 meters per second. Okay, so here's our formula. And the first step is to determine what's moving. Well, the source, so the ambulance, is moving, but the observer is stationary, so I can cross that out. I don't even need to put the plus or minus there, because if it's +0 or -0, it won't affect that velocity on the top. So we're already done with step 1 right there. For step 2, we have to determine if this is going to be a higher or lower frequency. Well, if the ambulance is making these sound waves and they're coming towards the person and the ambulance is moving towards the person, then this is the same as if the person was running towards it. They're moving together relative to each other, so the frequency we hear should be higher than the frequency of the ambulance. So that means that this whole ratio then, for our step 3, has to be greater than 1. So let's fill in our values to see how that's gonna happen. We're trying to figure out what we're gonna hear it at. We know speed of sound is 343 meters per second divided by 343 meters per second, and the velocity of the source is 15 meters per second, and it's emitting a frequency of 550 hertz. Now there is brackets here in this formula. We just wanna figure out if we add or subtract that 15. Well, if we consider that 15 isn't there, that's just equal to 1. So we want to make this number greater than 1. Should we have the lower number bigger or smaller? The answer is we need it to be smaller. We want a bigger number on top so that this ratio is greater than 1. So I need to subtract 15 here. I'm going to take 343 divided by, this number is going to be in brackets, 343 minus 15. Let's see what we get there. 343 minus 15 gives us 328. So we'll go 343 divided by 328, and we get an answer of 1.045, which is what we wanted, a number greater than 1. It's not much greater than 1, but it is greater than 1. And then we're going to times that by the frequency that it was emitting, which was 550 hertz, and we get an answer of 575.15. Okay, and lastly, we'll round that. It looks like we only had 2 digits here because of the 15 meters per second. So this is going to be 5.8 times 10 to the 2 hertz. Okay, sometimes a bit harder on the bottom to think if we should plus or minus to make it greater or less than 1. If you got an answer here that was something like 530 hertz and you know that it was lower, and that wouldn't be right because they're moving together, you just go back and flip the sign. So these definitely take some practice, as there's more thought going into how to apply these equations than I think some other ones that are just plug in and solve. So make sure you do try those, check the answer key, and let me know if you have any questions, and I will see you in the next video.